Okay, example 4 on 4.3, this is the last example for 4.3. Given p of x equals 2x times the square root of x squared plus 1, same question they've been doing, increase, decrease intervals, maximum, minimum values of f, intervals, concavity, inflection points, and they want a part D here, they want to sketch the graph based on what we get from A, B, and C. So basically our inflection points, our maximum point, our minimum point, whatever those are going to give me some points we're going to get. And if we know the increase and decreasing and the concavity, then we can probably get a pretty decent sketch of this graph. First off, 2x times the square root of x squared plus 1, there is no interval, right? So there's no comma, some interval here, so there's no endpoints. Radicals do have undefined issues sometimes. We can't take the square root of a negative number, so we have to consider that likelihood in a problem of this variety. I'm going to probably just cut that on a new page. I'm just assuming that it's going to take some space to do this problem, so give myself some space there. So, first off, I would probably differentiate first and second derivative of this thing. And again, this is a scratch sheet of paper task. I want p prime of x equals something. I want p double prime of x equals something. Everything I do to get the derivatives, I would do on a scratch sheet of paper. For me personally, I like my derivatives in simplest form possible. So, imagine I've got a scratch sheet of paper right here. P prime of x. Keep in mind that p of x is this, right? And p of x, if I were to write it out in a better form, I'd rather have a fractional power than a radical if I'm going to differentiate. The structure of p of x is a product. We have 2x being multiplied by x squared plus 1 to the half power. D1 is going to be 2. D2 is going to be a chain rule, right? So again, looking at structure of things, how to differentiate. So product rule, because I have something times something, 1d2 is going to be 2x. D2 is going to be 1/2 times x squared plus 1 to the negative 1/2 times 2x. The power, base to 1 lesser power, derivative of base. Plus 2d1 is going to be plus x squared plus 1 to the half. D1 is going to be times 2. So, just take a look. There's 1d2 plus 2d1. Again, product rule, we're expecting 2 terms out of it. What I do at this point is simplify as much as possible, because again I want p prime of x simplified as much as possible. That 2 cancels that 2. That square root of x squared plus 1 goes in the bottom. So p prime of x is going to be 2x squared on top, the square root of x squared plus 1 on the bottom. And this is going to be plus 2 times the square root of x squared plus 1. One last thing I'd recommend, because again we want to get that equal to 0, right? We want to find out and find all that kind of stuff. One last thing I would recommend here. When you get a problem looking like that to begin with, it's a lot better if you make this into a single fraction with a common denominator. Just is. We're going to get 2 objects. One's going to be a fraction because it's this negative half power. Anytime you have just a basic root, it's going to be like some normal fraction between 0 and 1. When you differentiate, you're going to get a negative power, puts that on the bottom. Okay. If I get a common denominator here of the square root of x squared plus 1, multiply top and bottom by the square root of x squared plus 1. The effect on the bottom is pretty simple. You get the square root of x squared plus 1, the common denominators there, right? The effect on top is really nice because these are exactly the same, right? If you multiply the square root by itself, you get a non-square root. So my p prime of x becomes 2x squared plus 2 times x squared plus 1 all over the square root of x squared plus 1. Again, this times this makes the x squared plus 1 no radical. X squared plus 1 is more than one object, so I'm putting parentheses around it because 2 is being multiplied by this product, so 2 needs to be multiplied by every piece of that product. If I distribute the 2 through and add like terms, we're going to end up with 4x squared plus 2 on top, square root of x squared plus 1 on the bottom. That's the easiest, most structurally sound p of x I could possibly make, or p prime of x. So 4x squared plus 2 over the square root of x squared plus 1. Again, that's all scratch work. I would expect, and again, if you want with this one without the fix, that's fine. You'd have to differentiate this. That's a quotient rule, that's a chain rule. You'll get a more complicated. Here I've just got a quotient rule with the chain rule mixed in. So it's better, but again, you can work with either one. So once you get that figured out, again, on a scratch sheet of paper, so this doesn't even exist anymore to me because I just threw it out. There we go. All right. So then I move on to second derivative. If I'm doing a second derivative, I start at first derivative, p prime of x equals, I would write it as 4x squared plus 2 on top over x squared plus 1 to the half on the bottom. This is a quotient, so I have to use a quotient rule to differentiate. Low d high minus high d low. The d high is easy because it's just a polynomial function. D low, I have a chain rule happening, right? So, p double prime of x equals. Low d high is going to be x squared plus 1 to the half times 8x. Minus high d low is going to be minus 4x squared plus 2. D low is going to be 1/2 times x squared plus 1 to the negative 1/2 times 2x. Over the square of what's below is just going to be x squared plus 1 to the first. Alright, and again, it makes this expression, it's a big mess, but we're going to have to fix it, make it as pretty as possible. First off, this 2 and that 2 cancel. All this stuff's being multiplied here, so that half and that 2 make just x. That negative half power belongs in the bottom in that area, so don't bring it to the bottom, but just within that expression, bring it to the bottom. This x is being multiplied through there. It's actually negative x being multiplied through there. I would probably change my half powers back to square roots. So p double prime of x, I just circle some things in color here. That piece there is going to be 8x times the square root of x squared plus 1. For right now, that's as pretty as I can make that. This thing here, which is all this stuff being multiplied together, 4x squared plus 2 is being multiplied by x. I'm going to make this a plus sign because I'm going to deal with the minus sign through the multiplication. Minus x times 4x squared is minus 4x cubed. Minus x times 2 is minus 2x. All that's over the square root of x squared plus 1. That's my top, and then over x squared plus 1. And again, this is a pretty standard thing that happens in these radical things. When you do a quotient rule with a radical involved, you're going to get a term kind of looking like this every single time. Multiply this, this, and this all by the square root of x squared plus 1. This goes away. That becomes an x squared plus 1. No radical. This becomes an x squared plus 1 to the 3/2 power. So basically, I'm taking the entire top by the square root of x squared plus 1. Taking the entire bottom times the square root of x squared plus 1. Notice here I'm multiplying by a square root form. Here I'm multiplying in fractional power form because that's easier to simplify. So I get p double prime of x equals. Alright, so the red term becomes 8x times x squared plus 1. The square root of x squared plus 1 times square root of x squared plus 1 is just x squared plus 1. 8x is being multiplied by this, so 8x has to be multiplied by the entire product, so parentheses are required there. This times this, the square roots of x squared plus 1 cancel, so I'm just going to get minus 4x cubed and minus 2x. And on the bottom, x squared plus 1 to the first times x squared plus 1 to the half makes x squared plus 1 to the 3/2. And then finally, combining like terms, do the distributive property, all that stuff, finish out the algebra. And that's 8x cubed plus 8x. 8x cubed minus 4x cubed makes 4x cubed. 8x minus 2x makes plus 6x. All over x squared plus 1 to the 3/2 power. And that's the simplest second derivative I can possibly make. So every time you do these problems, that's priority 1. You want this thing to become a first and second derivative. Again, all this work here, spare sheet of paper. Okay, I don't need to see all that stuff. I'll believe that you did it with your ingenuity and your brilliance to get to that point. All right. Once you get the derivatives, Then we want to find these intervals. Okay, intervals of increase, decrease happen at critical numbers. Critical numbers happen at 3 criteria. Criteria 1 equals 0, first derivative. First derivative is undefined or endpoints. Okay, so looking at parts A and B, that's all about the first derivative. I'm going to consider this here. First derivative. Criteria 1. When you have a rational function, and you want to find out when a rational function, that means a fraction, when you have a fraction, when you want a fraction equals 0, the top equals 0. Okay? So for criteria 1, I want this fraction equals 0. I simply ask myself, does 4x squared plus 2 equal 0? Where does that happen? All right, so when does 4x squared plus 2 equal 0? Try solving it. When does 4x squared equal negative 2? When does x squared equal negative 1/2? Because divide both sides by 4 and reduce. So when does x squared equal negative 1/2? There's a word that starts with N, rhymes with forever. It's 5 letters long. What? Never, never. X squared can't equal negative 1/2 in the real world, right? We don't graph imaginary numbers. All right, so x squared can't equal negative 1/2. That's not possible. Or if we'd even gone up here, 4 times x squared is going to be 0 at least, right? You take 0 and add 2, you get 2. You take something bigger than 0 and add 2, you get something bigger than 2. It can't equal 0. It's not possible. Not in the real world. So the fraction cannot equal 0. So there's no critical numbers based on it equals 0. The second criteria is the derivative is undefined. Derivatives are undefined, rational functions are undefined if the denominator equals 0. Okay. So again, if you get a rational structure, which happens a lot, like I'm saying a lot, like if there's 50 problems, it's going to happen in 23 of them. It's a lot. Okay? You get a rational function, top equals 0 deals with criteria 1, bottom equals 0 deals with criteria 2. That's the undefined. All right? When does the square root of x squared plus 1 equal 0? The square of both sides, you get x squared plus 1 equals 0. When does that happen?
Never.
Never. There we go. That N word again. There are absolutely no critical numbers for the first derivative because there's no endpoints either, right? So that's kind of boring. There's no critical numbers. That means it's either always increasing or always decreasing. All right? So from negative infinity to infinity, there's my interval that I have to deal with. I need to figure out what's happening to this function. So I have to figure out if the derivative's value is positive or negative on that interval. Again, it never changes. So I just have to pick a number between negative infinity and infinity. Something you want to pick?
0.
0 is good. All right, if I put 0 in for x, I'm going to get 0 plus 2 on top. I'm going to get 0 plus 1 is 1, square root of 1 is 1 on the bottom. 2 over 1 is positive, right? So it's always increasing. You can say always increasing or increasing on negative infinity and infinity. Either one of those mean the same thing. This graph always increases, never decreases. If it always increases, it started somewhere, right? And it comes up, and it continues up forever. So there's no bottom, there's no top, there's no maximum, no minimum. So part A, done. Part B, no max or min. Maximums happen when you go up and then you start going back down. Minimums happen when you go down and start going back up. If you always go up and never go down, you never hit anything. Okay. I'm assuming the bottom of the graph is negative infinity, the top is positive infinity. I don't know what that is, so I can't make it become something. All right. Hopefully the second derivative gives us more information. Is everybody okay with all the first derivative stuff there? You just take all the work and you shrink it down into a small little box and slide it over there out of the way. Moving on to second derivative, that will be question C. Intervals of concavity and inflection point. So again, what kind of structure is this? Right here? What do we call it when we add a fraction? Starts with R.
Rational.
Rational, so rational expression. And again, the criteria for critical numbers equals 0, undefined endpoints, right? Rational functions equal 0 when the top equals 0. So 4x cubed plus 6x equals 0. If I try and solve this, I can take a 2x out of the expression, right? So that gets me 2x squared plus 3. 2x is the greatest common factor. 2x squared plus 3 is left over. At this point, I have a factor equal to 0, so either factor 1 equals 0 or factor 2 equals 0. Bless you. All right. When does 2x equal 0?
When
X equals 0.
X equals 0. When does 2x squared plus 3 equal 0? Yeah, very good. It's the same time 4x squared plus 2 equals 0, right? X squared 0 at least, or bigger, times 2 makes it 0 or bigger, add 3, now you're 3 or bigger, number equals 0. At least we got a critical number this time. 0 is a critical number. All right, look at the bottom. We want the bottom equal to 0. That's going to be x squared plus 1 to the 3 halves equals 0, which means x squared plus 1 would have to equal 0, right? When does x squared plus 1 equal 0?
Never.
Never. So we got a critical number out of this one. So from negative infinity to 0, there's some sign. From 0 to infinity, there's some other sign. Maybe. Sign change can occur whenever the derivative equals 0. I want to determine the value of the derivative at each of these things. So I'm going to get negative 1 and positive 1 as my numbers. If I put negative 1, I'm going to get negative 4 minus 6 makes negative 10 on top. 1 squared is 1, plus 1 is 2 to the 3 halves power. I have no idea what negative 10 over 2 to the 3 halves power equals, but I do know it's negative, right?
Yeah.
That's all I care about is whether it's positive or negative. If I put positive 1 in, positive 4 plus positive 6 makes positive 10. 1 plus 1 is 2 to the 3 halves, that's positive. Just like that, I can see that it's going to be concave down. From negative infinity to 0, it's going to be concave up. From 0 to infinity, which means there's an inflection point at 0 comma something. Right. If the concavity switches, there's an inflection point. 0 comma something, how do I find the something?
Put 0 into the original.
We're trying to graph this. We're always trying to graph p of x. So once we get values, critical numbers, specifically to the first or second derivative, anytime you get a critical number, that critical number goes back into p of x to establish an actual point on the graph, which is going to be a maximum, minimum, or inflection point. So if I put 0 in place of x here, 0 times 1 makes 0, right? So 0, 0 is a point. That's promising. We did all that work, we found a point. All right, but we also got information about concavity, increasing, all that kind of stuff. So we got a lot of information, but we only got 1 point out of this whole thing. This happens a lot. You do a lot of calculus, you get a bunch of information about concavity, increase and decrease, and that's great information. But ideally we want to plot points, right? We want to find points, we want to graph this thing. We only got 1 point out of this whole mess. So what we do, if we only find 1 point, is we go back to basic math, basic algebra, basic anything. Make an XY chart. I already know that 0, 0 is a point on this graph, right? And specifically, its importance is that it's an inflection point. Okay, so XY in importance. That's what I would have in my chart. All right, 0, 0 is an inflection point. That's the only important point I got. If I had some maximum, let's say 2 comma 8 as a maximum, 2, 8 max, and negative 3 comma negative 12 is a minimum, negative 3, negative 12 minimum. So as far as importance, inflection point, maximum, minimum, that kind of stuff will be important, right? Beyond that, there's no important points. So how do you find more points? Pick more x's. Any x's that you think of that you really want to use here? 1? Sounds good. Anybody else?
Negative 2.
Negative 2, probably good. Pick numbers near the important point. If you got like 3 important points, you want to get more points, pick numbers near those. All right, so 0 is x, picking numbers near that, negative 1 is probably a good one, 2 is probably a good one, 3, negative 3. All right, and the way we get these coordinates is we open up our calculator, which I wish had already been opened. Now we got to wait for it to open. And go back to my graph here, my equation, and type in this equation on my calculator. So 2x times the square root of x squared plus 1 in parentheses. And I'm going to go to second table. And I'm going to go back over here and I'm going to evaluate the function for these numbers. So 0, of course, 0. We got 1, negative 2, negative 1, 2, 3, negative 3. Oops. All right, so a couple decimal places is plenty because we don't, I mean, if I graph 2.8284 and 2.83, eyeballing it either way, so it doesn't matter. So 2.83, negative 8.94, we got negative 2.83, we got positive 8.94, we got 18.97, negative 18.97. Anybody want to graph 18.97? Me neither. Okay. If you get some points you don't like, pick some different points. So I think 8.94, negative 8.94 is probably big enough. Maybe if I picked like a 0.5 and a negative 0.5. It doesn't matter what I pick for x because my calculator is evaluating for them anyway. So negative 0.5, 0.5, negative 1.12, and positive 1.12. That looks more reasonable, right? Maybe I threw some 1.5s in there also. Got room there. 1.5, negative 1.5. 5.41, negative 5.41. Now that I got those points, I don't want to graph these 8.94 either. All right. You pick and choose. What do you want to graph? You got graph paper there. I went all the way up to 1.5. I'm looking at my graph here. I've got plenty of space. Maybe I'm going to go, let's go to 0.25 scale on x, and let's go, oops, 2.5. I'm going to go to 1 scale on y, because I can fit those numbers on there, right? 5.41, 1, 2, 3, 4, 5, 6. Yep, I can fit that on there. So, 0, 0 is an inflection point. And 1, 0.25, 0.5, 0.75, 1, 1, 2.83 would be about here. Negative 1, 0.25, 0.5, 0.75, 1, 1, 2.83 would be about here. 1.5, 1.25, 1.5, 5.41, 1, 2, 3, 4, 5.41, a little bit less than a half. Negative 1.5, 1, 2, 3, 4, 5.41 would be about here. 0.5, 1.12, negative 0.5, 1.12. Okay, I got some dots there. And it either gives me a clear picture of what I'm supposed to graph or it doesn't. All right, if it does, fine, go ahead and connect dots. If it doesn't, pick more points. Pick 0.25, 0.75, 1.25. You know, get more dots. Get as many dots as is necessary for your brain to piece it together with the other information we have about this. It's always increasing, so it's always getting bigger, right? It's concave down to 0, 0, then it's concave up from 0 to infinity. That's what we found out, right? Concave down here, concave up there. I can kind of see a little curvature downward, a little curvature upward. Again, if I got enough information, fine. If not, get more points. So, based on the evidence I found, there's my concave down. There's my concave up. That's kind of what I think it looks like. Again, if that wasn't good enough, oops, that wasn't good enough for me. Again, if I look at that picture, my brain's not wrapping itself around that enough, then again, I've just come over here to my chart. Pick some more points. X, Y, 0.25, 0.75, 1.25, negative 0.25, negative 0.75, negative 1.25. Again, I got room on my graph to get more points, right? Just put it in my calculator. Again, I can pick any x's I want. My calculator's doing all the hard work for me. It's evaluating it. 0.25, 0.75, 1.25, negative 0.25, negative 0.75, negative 1.25. So we get 0.52, 1.88, 4.00, negative 0.52, negative 1.88, negative 4.00. So if I plot those, 0.25, 0.52 would be about here, 0.75, 1.88, 1.25, 4.00, negative 0.52, negative 1.88, negative 4.00. And you get more dots, you get a clearer picture of what it's supposed to look like. It's up to you. You pick as many dots as necessary for you to see the picture with the information. Concave down, concave up. It's curving downward, it's curving upward.
That's kind of cool.
All right? That's what graphing is. It's just a matter of, you can pick a million points if you want to. The purpose of calculus is to make it be fewer points to have to pick to get what you're looking for. That's what we do it for. So that will be the end of that as far as I'm concerned. That deals with that. Takes care of any connected dots very well.